Hey everyone, welcome to today's Explainer. I'm absolutely thrilled you're here, because we're about to pull back the curtain on, well, arguably the grandest computational illusion of the modern age. We're literally going straight down to the bare metal of our machines to completely shatter the illusion of perfect mathematical certainty in modern AI. Trust me, this is going to fundamentally change how you look at the digital infrastructure running our world.
All right, let's jump right in with a question that kind of challenges our everyday assumptions. Do computers actually process meaning? Think about it. When you type a complex prompt into an AI, it feels like the machine actually understands you, right? Like it's dealing in absolute facts, grasping language, and spitting out mathematically perfect results. But the reality? The reality is way more chaotic than that.
Get a load of this. 80 to 90%. That is just a staggering number. It's actually the percentage of modern AI compute cycles that are merely hardware-level approximations, not exact math, approximations. When these massive language models do their heavy lifting, they aren't calculating some absolute ground truth reality. They're fundamentally just guessing, trying to find the nearest mathematical truth that fits into a highly compressed physical space.
So, Section 1. The Grand Computational Illusion.
And the core problem here is perfectly captured by researcher Kyle McLean-Smith. He says it's fundamentally an approximation system, not real arithmetic. And man, that just hits the nail on the head, doesn't it? The physical engine driving your incredibly advanced AI is literally physically bound to make highly educated guesses. Why? Just so it can process massive amounts of continuous data at those blistering speeds we expect.
Moving right along to Section 2, Descent to Bare Metal. Now here's the crucial point about the basic phenomenology of arithmetic, the actual physical reality of the math. Down inside the wires, there are absolutely no semantic symbols. There's no meaning, no context, honestly, not even ones and zeros in the way we usually picture them in our heads. The machine is utterly blind to our intentions. It literally only understands physical resistance and continuous electrical currents marching to the strict internal metronome of timed execution cycles. High voltage, low voltage, all driven by a strict, relentless mechanical clock. That's it. That is the stark reality at the bare metal.
And this leads us to a massive physical divide. On one side, you've got human cognition, what researchers like to call wet code or OS alpha. It's warm, it's messy, it's highly associative, and just flowing with continuous meaning. But on the exact opposite side, we have the dry code of the silicon hardware. Unapologetically cold, rigid, and demanding discrete exact execution, with zero inherent meaning. It's a huge modality mismatch. We're essentially trying to force a flowing river of human thought through a rigid, square mechanical grid.
Which brings us to Section 3, FPU Gambler versus ALU Surveyor.
So, inside a computer's physical brain, there are two radically different ways to process reality. On the left, we've got the floating point unit, living in this heuristic, approximate world of flops. We can call this the FPU Gambler. To process heavy AI math incredibly fast, it essentially just throws darts at a dartboard. It's highly probabilistic and lossy. But on the right, we have the arithmetic logic unit, the ALU Surveyor. And the Surveyor deals strictly in exact, deterministic, universally verifiable hardware truths, a world where 1 + 1 equals exactly 2 every single time. The crazy part, right now, modern AI relies almost entirely on that wildly guessing gambler. And by relying on the gambler, we introduce this absolute plague of hardware non-determinism. See, because the FPU is trying to squeeze continuous numbers into fixed bits, it constantly drops these tiny fractional bits. Now, dropping a 23rd decimal bit might seem harmless on its own, right? But AI is billions of concurrent operations stacked together, so these microscopic rounding errors violently compound. And it gets worse. Chip manufacturers use totally secret proprietary seed tables burned right into the silicon to help the gambler guess. Because of this, getting exact one-to-one mathematical reproducibility across different machines, like, say, between an Intel chip and an ARM chip, it becomes physically and mathematically impossible. No way around it.
Let's take a look at Section 4, the wood chipper effect.
Here's the mechanical process of what researchers actually call the wood chipper effect. First, the AI ingests exact source data. Could be a copyrighted book, a financial ledger, whatever. Second, the FPU Gambler approximates the math using those secret silicon tables we just talked about. And third? Well, because that math was just a lossy guess, the original provenance is irreversibly destroyed. The Gambler basically acts like a giant blender. You know exactly what fruit went in, but you absolutely cannot reverse engineer that smoothie back into its exact original components. The chain of title is just gone forever.
So how do we fix this? That's Section 5, the semiotic bridge.
To cross this terrifying gap between the wet code and dry code, we use something called the semiotic bridge. This is the use of strictly formatted text, think JSON, Python, or WebAssembly, acting as a universal, deterministic interface. See, text isn't just for human communication anymore. It's this divine script that safely compiles our fluid associative imagination directly into exact physical hardware execution, all without relying on that fuzzy guesswork.
By using this bridge, we can intentionally eliminate the gambler. How? By shifting our core computing logic strictly back to the ALU surveyor. A brilliant example of this from our source material is Grok's Language Processing Unit, or LPU. They achieve a completely software-defined deterministic computing paradigm by literally physically removing dynamic hardware schedulers and reactive components from the chip. Instead, the software compiler explicitly orchestrates a predetermined script, and the spatial stream programming model perfectly executes it on the hardware. It's purely deterministic. The machine knows exactly what it's going to do on every single cycle, giving us that rock-solid, predictable arithmetic.
Which takes us to Section 6, Architecture of Intelligent Capital.
The ultimate application of the surveyor in the real world looks a bit like this: the pseudo-swap automated market maker. It operates on what cryptographer Nick Szabo calls the vending machine primitive. You put an asset in, you get an asset out, based strictly on mathematical bonding curves like linear or exponential constants. There is no human judge deciding if you deserve the trade. It's just a smart contract executing purely discrete ALU-driven logic with absolute undeniable certainty.
And relying on the ALU surveyor like this financially liberates companies. When trust is mathematically baked right into the hardware via deterministic execution, you completely eliminate what the industry calls the mask rendering cost of narrative trust. You know, that hidden tax companies always pay, the endless legal fees, compliance delays, third-party audits to prove who owns what. When you eradicate the gambler's guesswork and lock in exact hardware determinism, that metabolic cost drops to near zero. And that unlocks this frictionless, exponential, superlinear growth for intelligent capital.
So as we integrate these incredibly powerful systems deeper into our finances, our legal frameworks, and our physical infrastructure, we face a massive choice. In the future of high-stakes computing, will you settle for the gambler's guess, letting probabilistic noise dictate your reality? Or will you demand the surveyor's exact truth, insisting on forensic accountability and absolute determinism? The architecture of the future is entirely up to what you demand from the metal. Thanks so much for joining me on this explainer. Keep questioning the systems you rely on, and until next time, keep learning.